What a beautiful face I have found in this place that is circling all around the sun. What a beautiful dream that could be in a blink of an eye and be gone from me. Soft and sweet, let me hold it close and keep it here with me.
Yigga, I don't understand this. Like, her website makes no sense. Can you help me with chemistry?
Okay, I'm on my way.
Oh, thanks, Yigga.
Hey Kevin, let's start chemistry! So, chemistry?
Yeah.
Kidding. Also, I brought Shun.
With me.
Okay, so what do you actually need help with?
Well, you see, I have this acids and base system I haven't started studying for you guys.
Well, that's pretty basic!
Well, I don't feel neutral about this subject.
No need to be salty, Kevin.
Before we begin, let's clear up what are acids and bases. There are three definitions accepted by the scientific community. The most basic definition, the Arrhenius theory, proposed in 1885 by Svante Arrhenius, defined an acid as a substance that produces hydrogen ions when dissolved in water. He defined a base as a substance that produces hydroxide ions when dissolved in water. While these definitions are incomplete, we can use them to describe the properties of acids and bases. Let's go to Kevin's basement to look at the physical properties. Firstly, both are electrolytes. Electrolytes are substances that produce ions when dissolved to form an aqueous solution. Since they have mobile ions in this state, both acids and bases are conductors of electricity.
So, Kevin, tell us, what can we use electrolytes for?
Well, Sean, being the genius that I am, I've completely overridden all of the lights in this room. You see, I'm going to use this solution here to conduct the electricity through these wires. So, well, that didn't work. Maybe the solution just isn't conductive enough.
Kevin, what did you do? All the lights won't turn on anymore!
Well, you see, I'm trying to prove that acids and bases are conductive in solution! Sean, why isn't it working?
Well, your solution seems to be neutral.
Neutral? What does that mean? I just put an acid in a base.
At the same time.
Well, yeah, 2 times the number of conductors means 2 times the conductivity, right? Right?
Strong acids and bases neutralize each other when they react in equal stoichiometric ratios. This happens since the hydronium ions produced by the acid and the hydroxide ions produced by the base bond with each other to form water, a neutral substance. At the same time, the parent anion in the acid bonds with the cation of the base to form a salt.
Hydrogen can be used to show the gradual process of neutralization. In this demonstration, hydrochloric acid is reacted with sodium hydroxide, 2 solutions of equal concentration. As sodium hydroxide is gradually drained into the solution of hydrochloric acid, the product becomes more and more neutral. We've added phenolphthalein to the solution to indicate approximately when the neutralization tipping point occurs. Here, at the moment where the solution turns pink, the acid and base have perfectly neutralized each other. As we add more base into the reaction, the solution is now more basic than acidic.
When a solution is neither basic nor acidic, it's neutral. The degree of acidity is measured by the logarithmic scale of pH, which stands for power of hydrogen. It's basically a measure of the concentration of hydrogen in a solution. A solution that is neutral has a pH of 7. Any number below 7 is acidic, and any number above it is basic. For example, we have extremely acidic and extremely basic substances with pH values of near 0 and 14 respectively. In the middle, we have water, which is generally neutral. Indicators such as phenolphthalein change color depending on the pH of the solution they come in contact with. They can be used to determine whether a substance is basic or acidic. Here's a table.
As a general rule, we can say that neutral solutions do nothing to the indicator. Acids provoke warm colors, and bases provoke cold colors.
Acids have sour tastes. A lemon is a good example of this. Bases have a bitter taste. Coffee is an example of a base. Concentrated acids and bases do have the chemical properties of being extremely corrosive, especially strong acids and bases, which ionize and dissociate respectively at 100%.
Many concentrated bases are used in industrial cleaners such as Clorox, and can cause severe burns and inflammation to skin. Of course, we have to remember that depending on their pH, they can also be relatively harmless. A plus side to bases is that they're slippery. An example is soap. Soap are bases which make use of mild corrosiveness to clean. Now that that's cleared up, let's move to a few more important signature reactions of acids. Acids also react with metal carbonates to produce carbon dioxide, water, and a salt. Here, the cation in the carbonate compound binds to the negative anion of the acid. Meanwhile, the carbonate ion and the hydrogen ion produce carbon dioxide and water. Another gas test can be used to demonstrate the gas product. If we approach a flame to carbon dioxide gas, the flame will be extinguished.
In this demonstration, hydrochloric acid is reacted with calcium carbonate in order to produce water, calcium chloride salt, and carbon dioxide. Acids react with active metals to produce hydrogen gas and a salt. This is exactly what happens when we react magnesium metal with 0.3 molar hydrochloric acid to produce magnesium chloride and hydrogen gas.
There's an easy way to detect hydrogen gas, commonly called the pop test. When a flame is brought into contact with hydrogen gas, a loud pop can be heard. With enough hydrogen, this pop becomes a boom, and an explosive flame can be seen. Don't imitate this at home, kids, but we've decided to trap the produced hydrogen gas in a balloon. And now Shun will demonstrate what happens when we try to blow it up.
Hold it back. Hey you! Stop holding around!
Wow, thanks guys. I understand everything now.
Oh, sorry guys, I just missed the bus.